Welcome back, everybody, to episode 40 of the Quantum Science Seminar, which will today be about variational quantum algorithms. And if you have any questions, we would like to have them. Please send us your questions to quantumscienceseminar@gmail.com or use the YouTube live chat at the right or at the bottom of the screen. Please also note that there's a 30-second time delay between what you see as live on YouTube and between what we do. Please take that into account in asking your questions. And with that, I'd like to hand over to Andrew, who will introduce our speaker today.
Thank you very much, Sebastian. And yeah, it's a great pleasure to welcome today's speaker to the Quantum Science Seminar, Sabrina Maniscalco. Sabrina is well known as a leading theoretician in quantum dynamics, and especially for a wide range of contributions that she's made around non-equilibrium dynamics and open quantum systems. Sabrina completed her PhD at the University of Palermo in 2003 and spent time as a postdoctoral researcher in Sofia, Durban, and Turku before taking up a position as an associate professor at Heriot-Watt University in Edinburgh in 2011. From 2014, she was a professor at Turku University, and just in the last few months has moved to Helsinki and is in a superposition, as she phrases it, between Turku, the University of Helsinki, and Aalto University. One of the many impressive parts of Sabrina's work is the way that she builds new bridges between fundamental theoretical concepts in quantum information and practical applications to experiments, to quantum technologies more broadly, and indeed the way that she's led many projects and a lot of research in broader interdisciplinary projects. She'll be telling us more today about a new approach to variational algorithms for near-term quantum computers, and we're really excited to hear more about it. So Sabrina, welcome to the Quantum Science Seminar. It's great to have you with us.
Thank you very much, and thanks a lot for giving me this opportunity to present these results that are extremely new and fresh. And I will begin by sharing my screen, and I hope in a moment you will be seeing this presentation. Do you see? Yes, okay, fantastic. Thank you very much. So the title of my talk is Learning to Measure. I will talk about an adaptive, informationally complete POVMs scheme for near-term quantum algorithms. I hope this will become clear as I talk. I thought of giving a very simple introduction of the field and then go deeper in the results. And my attempt will be to, of course, try to keep everything at a sufficiently clear and understandable level for everyone to follow. But before doing this, I would like to acknowledge the people who actually worked with me at these results. And in particular, the Finnish team composed by Guillermo Garcia Perez, Matteo Rossi, and Boris Sokolov, all three postdocs, as Andrew properly said, in between Turku and Helsinki and all part of algorithmic as well. And then these results has been obtained in collaboration with the IBM quantum team in Zurich, Francesco Tacchino, Panos, okay, Bargozos, Guillermo Mazzola, and Ivano Tavernelli. Sorry for my pronunciation. Where it all began, actually, the interest we have been having on this type of problems began at a Qiskit camp close to Zurich, actually. And this is a picture of our team there. And this is the moment in which we started to brainstorm and discuss topics of this in this framework. And this is also the moment in which we met for the first time Ivano and his team. And so our initial discussions date back to then. But now, let's begin with the very general introduction, and I would like to begin very simply by talking about quantum computing. And I think that very, very broadly speaking, we can all agree on the fact that the goal, perhaps, of the whole emerging quantum computing ecosystem is really related to understanding if and to which extent, and also when, it will be possible to build a computing machine able to perform tasks which are impossible to conventional classical computers. And of course, we do know already theoretically that there exists quantum algorithms exploiting quantum properties of physical information carriers that outperform all currently existing classical algorithms. There are some examples of these algorithms. However, they run on ideal universal quantum computers, and this requires fault tolerance. So in a way, we should remember that while a quantum Turing machine, which is a universal quantum computer, is an abstract machine, which is used to model the effects of a quantum computer, and any quantum algorithm can, of course, be expressed formally as a particular quantum Turing machine, in reality, we all know very well that information is physical, and that physical realization of quantum computers are what we have to handle and deal with. Algorithms, in this sense, are dynamical quantum processes in quantum machines. And of course, this immediately leads us to think in terms of what is considered one of the enemies of quantum computers, that is decoherence. And I would say that we all agree that the main issue here is related to the extreme fragility of the quantum information storage and processing in presence of an external environmental noise. And because of these error correction techniques that are required to achieve fault tolerance are still experimentally in their infancy. There is a lot of theoretical works, we know a lot, but we still struggle to implement them in the experiments. So I would say somehow that from my perspective, this is my personal point of view, it is not yet 100% clear at the moment whether decoherence will be eventually a fundamental, unavoidable limiting factor in the manufacturing of universally scalable quantum computers or not. Most likely it's just a question of technology, it's a question of time, it's a question of resources, but there are still great challenges ahead in terms of building a fault-tolerant scalable quantum computer. And that's why we want to focus in the remaining on the talk on so-called NISQ devices, noisy intermediate scale quantum devices, a term coined by John Preskill not long ago in 2018. Actually, a lot has happened since then. And here, in a way, what we are doing is shifting a little bit the type of question that we are asking. What we are starting to ask now is, what are the useful problems that quantum computer can solve more efficiently than their classical counterparts, but more specifically, which subclasses of such problems are experimentally less demanding given the current state-of-the-art quantum hardware. So we are more focusing somehow on what is possible to do now with the existing devices, and to which extent somehow we need to modify what we have to prove some quantum advantage. I would say that there are two main lines when it comes to theories in this perspective. And the first one is, of course, quantum simulations. Both Yuri Manin and Feynman in 1882 pointed out that simulating quantum systems is hard on classical computers. However, one can use a quantum system to simulate other quantum systems. And this can be done both using analog quantum simulators and digital simulators. And of course, this is clearly lifting of some of the requirements of universal quantum computers, because we are now talking about specific purpose devices. And a second avenue to become closer to realistic devices is what I would say abandoning the exact. And just to make an example, while it is unlikely that quantum computers will be able to solve efficiently worst case instances of NP-hard problems, like, for example, combinatorial optimization problems, it might be possible to build specific purpose quantum devices able to find better approximate solutions, or perhaps find such approximate solutions faster. So here the emphasis is on abandoning the exact. And in a way, in between these lines of thought, a very recent and also particularly active field is the field of variational quantum algorithms. These are hybrid quantum classical algorithms that consist on a quantum part in which a certain quantum state is prepared and on a real quantum device and used to explore the exponential vastness of the Hilbert space. And then measurements are performed, and certain, using the outcomes of the measurement, classical optimization routines are used to update the parameters encoded in the initial state preparation. And this is used eventually to prepare an initial state in the next cycle. So in a way, they combine quantum and classical routines. And one of such algorithms is the variational quantum eigensolver, which has been extensively used, for example, in quantum chemistry. And here the main point is to minimize the energy of a many-body correlated quantum system. And we will, in this talk, focus on this problem and analyze a number of examples related to that. So again, the idea is we use the quantum device to explore the exponentially large Hilbert space of the fermionic particles in order to find in an iterative way the ground state of the Hamiltonian, importantly, without solving the full diagonalization problem, which is the real bottleneck here. Now, quantum chemistry Hamiltonians that we will use are examples are the one here shown. So why do we do this, and what is, sorry, I will, let me just use the pointer. Yes, I should be able to use it. So the knowledge of the ground state for a certain compound in chemistry is important, because if we study a plot like this one, where I have the energy as a function, the ground state energy as a function of the interatomic distance, for example, for H2, then I can use, if I reveal this behavior, it can be used to extract crucial information, such as, for example, the equilibrium bond length, bond angle, dissociation energy, and these are all very relevant quantities to compute and important, very often hard to solve computationally on classical devices. So one generally starts with the electronic Hamiltonian, and this is after the Born-Oppenheimer approximation, and here Ri is the position, identifies the position of the electrons in the compound, while this one is the position of the nuclei, and goes to second quantization. Now, in the passage to second quantization, I introduce fermionic operators AQ and A-DAGA-Q, and these describe excitations of one electron into the single electron spin orbital, P in this case, or Q. So now, this Hamiltonian is quite general, and it contains these two terms, and the coefficients HPQ and HPQRS are defined in this way. The first one describes the kinetic energy terms of the electrons and also their Coulomb interaction with the nuclei, while the second one is responsible for the electron-electron Coulomb repulsion. So this is a quite general Hamiltonian that is the starting problem, the starting point, sorry, of many VQE problems. The next step is what is known as the Fermion to Qubit mapping. So starting from this second quantization Hamiltonian, we want to obtain a Qubit Hamiltonian. And the Qubit Hamiltonian is generally obtained in terms of a weighted combination, linear combination of the so-called Pauli strings. So the Pauli strings are products of single qubit Pauli operators, the identity, and then sigma x, sigma y, and sigma z. And the coefficient Ck is known as the Pauli weight. This is the number of non-identity single qubit Pauli operators in a Pauli string. Now, depending on the mapping, on the Fermion to Qubit mapping that one uses, there are many. the Pauli weight changes. So in general, the most famous, at least the one I knew better when I approached this field, was of course the Jordan-Wigner transformation. This leads to a Pauli weight, which is linear in n. Other less known mappings are the Bravi-Kitaev and the very recently introduced Young mapping. The reference is of 2020. This is a paper by the Google group, which has introduced this mapping, which these last two are particularly interesting because the Pauli weight is only log n. So we will see that this is relevant actually and important for our results also to consider. And I will be very, very brief in describing the main features of these mappings. The first one is the Jordan-Wigner transformation, which stores the occupation number locally and the parity non-locally. Of course, the parity operators take Z in this case, take into account the fermionic character of the electrons. And then we have the parity transformation, it's a bit less common compared to the Jordan-Wigner transformation, in a way opposite, because it stores the parity locally and the occupation numbers non-locally. Then there is the Bravi-Kitaev transformation, is more complex and somehow find a midway point between the Jordan-Wigner and the parity method. So it compromises on the locality of the occupation number and the parity information. And then the last parity mapping that we will consider is the one introduced in this recent paper. Young is the first author, and is defined on ternary trees. What is interesting is that it maps any single Majorana operator of an n-mode fermionic system to a multi-qubit Pauli operator, which acts non-trivially on order log n qubits. So this will be very briefly reviewed. At this point, the first step of the VQE is the variational ansatz, and it has to do with the state preparation. In general, because we want to minimize the energy of the molecular compound, we want to think, or we want to create initially on the qubit device, on the quantum computer, a state which has a sufficiently large overlap with the target eigenstate, which is the ground state in this sense. And there are ways of doing this. There are problems, but there are also approaches that are differ, like hardware efficient ansatz or chemically inspired ansatz. There is a variety of them, and the field is growing and presenting more and more of them. But what is important to notice is that here the state prepared by a given circuit is obtained in terms of certain parameters. In this case, perhaps I don't know if you can see it well, but these rotations, for example, introduce the parameters theta. And then these parameters are used in the optimization. So after this preparation of the ansatz, a measurement is done. And in particular, one measures Pauli strings, that are these products of local Pauli operators. Here is the point. What we want to obtain is calculate an expectation value. So the expectation value of the Hamiltonian is calculated. And obviously, we need to repeat the measurements to accumulate statistics. At this point, the classical optimization by means of many different routines can be done. Gradient descent is one of them. And this ends up, so the state is then prepared for the next cycle. Now, to go back briefly to what is the impact of this of such an approach. Of course, one of the main regions, one of the main scopes of application of VQE has to do with solving classically intractable chemistry problems. This can be very useful, for example, for high temperature superconductivity, to understand biochemical reactions, to understand better and model transition metal catalysis. And of course, in turn, this can be used to design new compounds with applications, certainly in the whole drug design industry, but also in material sciences, for example, in the generation or engineering of new materials. Now, the roadblocks of variational quantum eigensolvers, of course, variational quantum eigensolvers is a heuristic approach, but it is more or less agreed that there are two main roadblocks. The first one has to do with the fact that the optimization procedure can become quite difficult in practice because of the presence of many local minima. So the configuration landscape where we optimize can be so rough that actually we might be stuck in the optimization in local minima. And of course, in a way, there are many classical approaches. One can use many classical tools or methods to minimize or to face this roadblock. And at the same time, there are several groups that have studied and discussed different types of how to improve the answers choice. For example, adapt VQE is one of such examples. And the second roadblock is the measurement problem. And I'm going to talk here in this specific, for the remaining of the talk, specifically on the measurement problem. So this will be my main interest. The measurement problem, in a nutshell, has to do with the fact that it turns out that if you want to use VQE for many interesting Hamiltonians, chemistry Hamiltonians, as we increase the size of the problem, the number of measurements needed, obviously in a regime in which VQE would be advantage with respect to the classical methods, is extremely large. So there have been estimates that it may take even years to reach the required precision. Often chemistry, people talk about chemical accuracy. That is an accuracy that is, for computational chemistry, what is needed to have good estimates of chemical quantities. We are now ready to discuss the main idea of the algorithm we are going to propose and then to present the results. But before, what is the key ideas of the learning to measure approach we devised? Well, the approach is actually what we think is a new perspective to look at the measurement problem and includes, so it is a method that we believe may alleviate sensibly the number of needed measurements and possibly pave the way to better feasibility with current experimental NISQ devices. And it relies on three main points. The first one is the use of informationally complete POVMs for the measurement. The second one is a hybrid quantum classical Monte Carlo sampling. And the third one is an adaptive measurement strategy that is used for learning actually the optimal way of measuring. Now, what is here the way of formalizing the problem we face? So consider now a given observable O, so a bit more general than just the Hamiltonian. The Hamiltonian is an example. So we can write it, express it in terms of the Pauli string, and the real problem with this that we face with this with the analysis of the error in the estimation of this observable is that the natural measurement scheme is suboptimal, and the reason is that the variance of the observable is really the sum of the weighted variances of the individual Pauli strings, and is expressed in this formula, where S is the number of measurements on each Pauli string. So the more Pauli strings, the better is the precision required to measure the observable O, okay? And there are strategies to sort of alleviate this problem, like the grouped Pauli method, which aims at identifying all the Pauli strings that can be measured simultaneously from the same data set. But of course, and of course, in this way, parallelizing obviously the measurements. But it turns out that this is not an efficient approach. The second ingredient, or the main ingredient that we will be introducing is the use for the measurement of informationally complete positive operator valued measurements. So what we do is that the price we pay is that we need to, in this case, introduce an additional qubit. So we double the number of qubits. And we, because in this way, this is the way of implementing the POVM, and we define with pi m with m equal to 0, 1, 2, and 3, the local POVMs of effects that we will be using in our method. Now, each effect is associated by definition to one of the 4 possible outcomes of 2-qubit measurements. So this is the probability outcomes associated to them. Now, what we will do in this way is we will use these POVMs in a double manner. We will use them for optimizing the measurement, and we will use them in a quantum classical hybrid Monte Carlo method. And the way in which, in a way, we exploit the POVM for the optimization is related to the fact that any unitary between the qubit and the ancilla leads to a different POVM. So we can parameterize the POVMs by changing the unitary itself. And obviously, the advantage of using this informationally complete set is that we can use these to estimate the expectation value, not just of the Hamiltonian, but of any operator of our choice. So how does this work? So let's start by describing the Monte Carlo quantum classical hybrid algorithm. So in a nutshell, what we do is to reduce the problem of measuring a linear combination of a large number of Pauli strings to a Monte Carlo integral. This is what we will do, okay? It's a reduction of problem. And to understand it, we can write explicitly now the Pauli strings in terms of the product of Pauli operators, as you see here. And then we express each Pauli operator in terms of the informationally complete, or in terms of the effects, pi mi. Okay, and this can always be done because, of course, these are our bases, informationally complete. And we can rearrange the terms in a way of leading to an expression for the observable O, which is just the weighted sum of pi m. Pi m is the product of the local effects on all the qubits, okay? So it's the product of the pi mi. Now, how is this advantageous? Well, the reason why this leads to an advantage is that if we can now look at the mean value of O, we can express it in terms of Monte Carlo sampling. So if PM is the measurement outcomes of the different effects, what we will do is build an estimator in the following form. So we repeat the measurements as time using the local POVMs, and in this way, we will sample from the probability distribution PM. So we build this probability distribution sampling, and this is in turn used to calculate this estimator. What is important is that the quantum part is really the probability sampling PM, and then for each value of M, we can calculate on our computer efficiently the coefficients Wm. So we sample the value of M and we calculate the coefficient Wm. And this can be done efficiently on a classical computer because it scales polynomially with M. The estimation error is defined in these terms and is what leads to a better and better estimation. So reducing this estimation error means getting closer and closer to the mean value O. So reducing the gap between the Monte Carlo estimator and the mean value of O. So what is, in few words, summarizing, we can estimate the weighted average of all the Pauli string simultaneously, regardless of whether they commute or not, okay? And this has two advantages. The first one is that it circumvents the tomographic reconstruction of quantum states, and also it naturally takes into account covariance between all these parallel measurements. So this is really the real statistical error. Then the next step is the POVM optimization. So what we want to do is to use a classical post-processing routine to navigate the space of POVMs towards a low variance one. So we want to go towards the values, the POVMs which minimize the variance in order to have a better and better estimate. And so therefore one does this by feeding the outcomes of the current POVM to the classical routine. And then eventually this uses them to, so the routine uses them to evaluate the variance of the new POVM. So this is in order to understand briefly how this works, we rewrite, so we define with gamma R the new local effects, these are local, and we write their variance in the following form, but it's the definition of their variance. Now, these are two terms. The second term is just the square mean values of the observable, and of course does not depend on the POVM itself. So what we have to minimize is this term here. The trick is again similar to before. We do another, so we are trying to minimize this term in a way that will use, again, a Monte Carlo algorithm. So the way of proceeding is now expanding the expression of these local effects, gamma R, in terms of the previous one, the one that we had already measured, the previously known POVMs. And we will rewrite this expression in this way. Again, we do have from the previous cycle the probabilities PM, and now we have to estimate this term. This is a little bit more tricky because it turns out that this term is not, can grow exponentially in the number of qubits, so it is not efficient to calculate on a classical computer. But using gradient descent, it turns out that we can solve this problem because only one of the terms in this product will be different from one. Okay, they will all be zero except for one. Okay, then next step. Actually, it is something to point out that in this procedure, in this adaptive procedure, we do not need to first optimize the POVM until it reaches a small variance and then start estimating the expected value, the observable. We can do this on the fly. So the strategy is to calculate a weighted average of the estimated means that minimizes the resulting variance in the estimation. And this is done in an iterative way. So we use the intermediate POVMs also in the estimation of the mean value. So all the data keep being used all the time. So the key ideas here are use of the informationally complete data of the POVM twice. First, to produce an estimation of the mean value of the observable. Second, to find a better POVM in the next experiment. This is key to understand why the measurement learning procedure improves over the initial POVM without, this is the important point, without no additional measurement costs. Now, before proceeding to show you the results on how it works, I wonder if maybe this could be a good time to stop for some questions.
Yes, thank you, Sabrina. We already have a bunch of questions. So the first one is from the very beginning. So you were starting about the coherence as an enemy of quantum computing in general. So the question is, it's always a real enemy? It cannot be exploited in some way in quantum computing protocols?
Yes, and of course, yes, we do know that there are strategies and techniques which exploit a careful manipulation of environmental noise, or even engineering of environment in order to actually achieve certain, for example, entangled states. However, it is still true that in all existing devices, there are sources of noise and error which are not even fully characterized. So while the truth is that it is true that noise can also be used and partly engineered in order to help us, for example, in entanglement state generation and so on, it is also true that the current situation of NISQ devices is situations where noise is really deleterious and needs to be characterized and suppressed, especially if the aim is reaching the threshold for error correction.
So then we have a second question. So it seems that one of the difficulties with a variational quantum eigensolver is that it is not usually possible to prove that this algorithm will have a scaling advantage over classical algorithm. Is that a problem, or is the point really to show an advantage over known methods for classical calculation in certain classes of use cases?
Yes, the second. The whole point is exactly to identify some use cases and some problems where there would be an advantage. Of course, it is true, it's a heuristic approach, and there is very little that can be shown exactly. I will show in the part of the results some examples of scaling, but this is generally we compare with the existing VQE approaches. But yes, the point is that I would say that really the goal at the moment that I think perhaps a lot of people are trying to reach is to prove that we can have a quantum advantage in a use case that is useful, for example, in the chemistry, for chemistry compounds, with respect to to what are all the known classical computational methods.
Another question, given the finite resources of current quantum machine, does it make sense to simulate fermions with qubits using any of the discussed transformation? Will it not make more sense to use fermions as a computational resource directly?
Sorry, I'm having a difficulty with my, okay, no, nothing. I have difficulties with my presentation, and then I got confused.
Don't worry, I can repeat the question if you want. So the question is that you are using qubits for simulating fermions with different kind of transformation. And the question is, will it not make more sense to use fermions directly as a computational resource?
Yeah, of course. I mean, very often you can use fermions directly. If you use fermion directors, generally, most of the examples I do know are examples in which that are in the class, in the framework of analog quantum simulators, while I would say that the framework of the digital quantum simulators is a framework in which you want to perform the simulation by means of a circuit-based, a gate-based model. And that's why the qubits, and that's why the formalism, and that's why it's also what is used really in the current small quantum devices.
Okay. Then we have a first question from Miguel in the chat. So typically, this sign problem is invoked as a reason for the lack of success in application of Monte Carlo to physical chemistry. Does the introduction of informational complete POVMs improve this aspect of Monte Carlo approach?
I would say yes, and I would pass also this question for more details to Guille, who should be also here. So I believe that maybe I go back, I will try to go back to the point, but Guille, meanwhile you can start answering, because I think that the main equation is this one. Yes, it's here. The sign problems appears. Guille, are you?
Yes, I am here. I don't know if people can hear me.
If I'm right, this is the problem where the sign problems can arise, and you can reply.
Yeah, this is indeed the case, that this term here, this one would need to compute this classically. And this involves many terms, because R here, the R parameter, R index here runs for up to 4 to the n terms. So in principle, if you want to evaluate that, you need to use a classical Monte Carlo-like approach. And the problem is that this product here can scale very badly. So this could be obviously a problem. So this is why with what Sabrina was explaining is that using the gradient descent, because these D terms there are the coefficients that represent the expansion of the new POVM that you are trying to kind of simulate classically, the gammas, in terms of the previous one that you used on the computer, the pi's. If you use a gradient descent, then you only calculate you only modify one of the parameters in the full POVM, And that means that you only modify the local POVM for one qubit. So this D is identity is equal to 1. Sorry, not identity, equal to 1. All these D's are equal to 1, except for one of the qubits. So then this scales very nicely because you only have 4 terms in the sum, and the product is just one number. So then you can compute this efficiently.
Okay, thank you for all the answer that you gave. I think we can continue, and we will keep some questions for later on.
Yes, I will be very glad to continue because I'm eager to show you some of the results. And the first results is actually some numerical simulation or numerical experiments of how the method works. So here I'm showing you 3 plots, and I'm showing you the adaptive measurement for energy estimation. So the plots you will see, I first describe them one by one. So the first plot is a plot of several quantities. I will describe them in a moment, but they all concern H2 with 8 qubits and with the young Fermion to qubit mapping. Then I have a second molecule with 8 qubit with the Bravy-Kitaev mapping, and then H2O with 14 qubits with a Young mapping. So what you are seeing here are estimated, these are the dashed, and actual, they are the solid errors in the estimation of the ground state energy. And these are shown, so the error is shown as a function of the number of experiments, of the number of shots, of the number of time you have to repeat, okay? And we are comparing here different strategies. The first one is just measuring the Pauli strings, that's the most straightforward. Then you will see the grouped Pauli approach, and then the POVM without gradient optimization, these are the green lines, and finally, the gradient, so the iterative adaptive measurement strategy with 2 different POVM as starting measurements. And you see in all of the cases, and by the way, and this line here is chemical accuracy. And you see that in all the cases, the adaptive measurement strategy works very well. It learns, it crosses even the best approach, that is the grouped Pauli in all of the cases. And in 2 of these cases reaches chemical accuracy. The 14 qubits, of course, it takes longer to reach chemical accuracy, and this is our limitations in the amount of time that we have to run, needed to run all this simulation. So the optimization works. It seems to work better and better as we increase the number of qubits. So you see the crossing point becomes for smaller and smaller numbers, overall total numbers of measurements. So I will show you now a video of somehow a visualization of the optimization strategy. So what you see here is the representation of the POVM on the block sphere, and you have 3 planes, XY, XZ, and YZ. So these black dots here represent the initial POVM that we use. And the video will show you how the POVM changes non-trivially, okay? And you have different colors because, of course, I'm plotting here different qubits. Here is the 8 qubits case. And you will see about 100 repetitions. So these clouds are because, of course, we consider, we repeat the experiments many times for statistical significance. And you will see, if you look specifically at the initial time, you will see how the changes occur. So you see, initially there is some movement, and now nothing happens anymore, and it stabilizes to the final values and to the final POVM, which is the optimal one used until now. And we have another example. This is an 8 qubit with the Bravy-Kitaev mapping. And again, you see here the initial values represented. Oh, I didn't want to do this. And here is the video. So it evolves non-trivial, and then it converges towards the optimal POVM. Okay, second part of the results, we would like to describe here the scaling, or to start studying the scaling. And what I'm showing here is the number of shots required to achieve a target error. This is actually smaller than chemical accuracy for hydrogen chains as a function of the number of qubits. So this is the number of qubits from 4 to 14, and this is the number of shots required to achieve a target error. And we know that this should be following this scaling with different coefficient B. And here you see the comparison between, again, Pauli and grouped Pauli, the SIC POVM, and clearly the better scaling of the gradient methods that I just described. And if we go and look at the values of the exponent, here in this table you have values of B, comparison between all these methods, and comparison for different mappings, Fermion to qubit mappings. And of course, the best one in our case is the one introduced by the Google team. And here we have a scaling exponent, which is on average 3.3. Okay, so it's definitely better than all the other considered methods, and the same as the reaches the level of the best techniques introduced in VQE. And finally, I would like to describe with you another important advantage of our method, which is the fact that we can use the same data obtained to calculate the mean energy for reconstructing the state, or for doing actually partial tomography. Here we have a partial tomography of 2 qubits, 3 qubits, and 4 qubits. So the reconstruction of the partial reduced density matrix of 2, 3, and 4 qubits. And here, unfortunately, you don't see the molecules. So this is done, I thought that I had added, but I didn't. This is done for 2 different examples that we considered before. Okay, I don't have them here. I can get back to you later. They are the 2 examples that we saw before with the same data, really. And this is the fidelity of the partial tomography. One is for the 6 qubit and the other one for the 8 qubit. And for the different, 2 qubit partial tomography, 3 qubit partial tomography, and 4 qubit partial tomography. The solid line is for the SIC POVM, and the dotted line, or the dashed line actually, is for our gradient POVM. So as you see, actually, with the same data that you used to estimate the ground state energy of the Hamiltonian, you can reach quite good fidelity. Okay, and I would say that with this, I would like to conclude my talk, and I would like to point out what I think are the main take-home messages. So the first one is that our measurement strategies seems to be very promising, and it uses an adaptive approach so that we learn iteratively what is the best measurement in order to find the minimal energy or the mean value of a given observable. It does not require exponentially scaling classical overheads, so computations. And importantly, it is completely agnostic of the nature of the qubit Hamiltonian. So we don't use any a priori information on the fact that, for example, the Hamiltonian is a chemistry Hamiltonian. It can be more general than that, and it is exact. Importantly, the measurement data can be reused to calculate other properties of the states, including tomographic reconstruction. So we believe and we hope that these results will be useful to understand what are the steps and to go towards a demonstration of a quantum advantage for useful use cases by means of variational quantum eigensolvers. And with this, I thank you for listening, and I'll be happy to answer to your questions.
Thank you, Sabrina, for the very interesting talk. We have a bunch of questions for you. So the first one would it make sense to consider machine learning to optimize the measurement protocol? Could one do much better?
Yes, I think that it might be possible to do it. And I do not know, however, whether it would be better or worse. So maybe actually Guille or Boris might answer, might have a more detailed information or more detailed idea about this comparison. Who wants to? Guille, Boris, do you want to?
Well, I can say something like really quick. We haven't yet started implementing anything, but of course we have ideas, and there are many developments in this well, in this direction. One thing that could be tried is like when you have when you collect statistics, you can use machine learning methods to sort of like create more samples out of your data, because then you can construct the distribution. And this, I think it has been tried before in some studies. But other than that, certainly it's a promising direction, but we haven't yet tried anything particular.
Okay, thank you. We have another question from Miguel. So in the hardware efficiency at SAT, it's been found that there can be a phase transition of sorts when optimized layer by layer, such that the predicted value suddenly changes. Have you observed something like that in the optimization of the POVMs?
No, we haven't for any of the cases considered. At least Guille and Boris confirm or not, but I don't think we have ever observed this. There is also another thing to mention, that this is just what we are describing is just one step of the VQE in itself. So it would be interesting to see how these incorporate. We think that it would lead to additional advantage as we consider the whole cycle. So Guille and Boris, what do you did we have numerically any evidence of this? I don't think in any of the cases considered.
No, we didn't. The thing is that in any case, it is still, I think, and also related to the previous question, I think the whole issue of the optimization of the POVMs in our work, I would say it still leaves a lot of room for improvement, either using machine learning or not. And also there is another aspect, which is that depending on the initial POVM, what we have observed, however, is that with different POVMs, we have more or less the same kind of performance, but the final optimized POVM, so once the algorithm converges, it's different. So it doesn't converge to a unique optimum. So this still raises the question of, okay, is there a global optimum that does even better than this? This would be very interesting, I think.
And certainly their machine learning approaches would be interesting to figure out, yes.
Okay, so the next question. You have used the example of digital quantum simulation, but if you have access to measuring Pauli strings, for example, in ion traps or Riebeck arrays, could you use this technique to optimize VQE using analog simulation in the variational part?
I think generally, we hope actually that this would be, we haven't thought about it, but I think that my main message is that is the way of thinking that could be used. I think definitely that it can be used in many experiments, also for analog quantum simulations. They are really adaptive strategies that rely strongly on the fact that if you use informationally complete data, and if you use this sort of hybrid quantum classical Monte Carlo sampling, you can achieve really a skillful optimization and learning of the measurement without additional measurement overhead. And of course, in a way, I would say that when the Hamiltonians are dense, it's probably when our algorithm works best. So when there are many Pauli strings, but okay, I would say that in general, my feeling is that it would be, I do not see, because it is a general approach and it is not only based on the choice of chemistry Hamiltonian. I think that it might be used also in other contexts, including analog quantum simulations. Yes.
So then we have other two questions from the chat. One is again Miguel asking if the Pauli string operators are obtained from Hartree-Fock orbitals.
Yes, this is. I think this is the general procedure of passing from the. I guess that there might be also many different ways or different ways of going from the quantum chemistry Hamiltonian to the qubit Hamiltonian. But I think that the standard is through the artifact method. Am I right, Guille, Boris?
Yeah, I guess the initial states are always obtained from the Hartree-Fock.
Then the second question from the chat comes from Roberta Zambrini, who is asking, results are theoretical prediction or runs on IBM computer?
No. This is, nothing has been run on the IBM quantum computers. They are numerical simulations. They are all numerical experiments. What we are studying are like 8, 12 qubits, 14 qubits. This would be, I believe, would be too noisy for at the moment on the current devices.
Okay, then we have another question. So he's asking, so the method seems a bit like a clever stepping routine used to solve a differential equation. How can you control the error in this method? How you verify the answer?
Yes, I think that this is, let me go. So you actually do have, because you have informationally complete data, you actually do have control and you do have an estimate of the error that you are performing. You are minimizing over the error you are performing, and you know, you can estimate the error you are performing. So you do know whether you go towards, for example, an eigenstate of the Hamiltonian. So it is what you cannot say is so let's say in the quest. So if you think in terms of whether or not you can say that you are in the global minimum, then of course you cannot say that you are really in the global minimum of the Hamiltonian. But by using skillfully your estimate of the variance, you could see whether you go towards an eigenstate of the Hamiltonian, for example. So this is a level of control that you do have, and it is due to the method itself is encoded in the method.
Okay, so then let's say a follow-up question, which is related to the last two. So how sensitive is the method on typical errors in NISQ devices? And how about long-range correlated errors?
I would say that, well, in the simulation, of course, well, I cannot say much about the correlated error. What I know is that what is useful is the fact that, of course, we are estimating at the same time with the Monte Carlo algorithms all the different Pauli strings. So in a way, in the correlations between the measurements of the Pauli strings, we have the real exact statistical error. But I don't know if this was the what he meant. Guille, what would you say about it? Probably this was the.
Yeah, for now we haven't, of course, taken into account any effects of noise. This is, of course, a very important point, especially considering that this is meant to be an algorithm for NISQ devices. So this, I don't know. It's a very good question. Of course, we need to explore this. Yeah.
But wouldn't you say that somehow the fact of, in a way, well, I don't know. One should consider it. I would sort of tend to believe that still, because of the way in which the total actually statistical error is estimated, it might be somehow the presence of correlations in the measurements. So the crosstalk, for example, about qubits might be, but I don't know. I mean, the truth is, as you said.
Yeah, we really haven't checked.
Yes.
Then I will conclude with a very general question. So you motivated that solving quantum chemistry problem is relevant for high temperature ITC superconductivity. In which sense do you mean this?
Well, I mean, okay. What I meant is mostly, oh, sorry, it got crazy. No, what I meant is that actually, if you consider that in the end, besides being quantum chemistry problems, what you have is systems, Hamiltonians of correlated and eventually strongly correlated fermionic systems, and this is the type of problem we want to solve. And in this framework, the application is not just for chemistry, but also for materials, and therefore any instance in which you need to describe or you need to estimate properties of strongly correlated fermionic systems would be definitely benefiting from the method. This is the framework, and this is the general perspective, yes, or the analogy.
Very good. So thank you, Sabrina, and Guy and Boris too for answering the question. And I let the step to Sebastian.
Thank you also from my side, Sabrina, for a very cool and interesting talk. And I would like to point out that next week on March 25th, we will have yet another talk, but it's going to be given by Yoshiro Takahashi, who will be speaking about quantum gases with 2 electron atoms. But Yoshiro will be giving his talk from Japan, so we will have to shift the time. So our seminar is not going to be at 5 p.m. next week. It is going to be at 10 a.m. Central European time. Please take that into account. You should also check out our sister seminar, the virtual AMO seminar, where tomorrow they will have Tanya Zelevinsky speaking about molecular clocks. And I would also like to remind you of our next hot topic session on April 22nd. Please send us your nominations by April 2nd. And if you want to get notified, please go to our website, quantumscienceseminar.com. You can subscribe to our email list, to our Google Calendar, and you can follow us on Twitter. And with that, I'd like to thank you for your interest, and we hope to see you again next week, same time, same place. Bye.
Thank you.